All right, this podcast we will be talking about some spanning tree related things. Spanning tree is a cool protocol that we have to keep frames from looping forever in a layer 2 network essentially. What spanning tree does is it blocks on some links and it forwards on some links. So that way we don't end up with a situation where loops can uh, travel all the way around the network forever. So in this case, we have all these switches on our network. They're connected in a redundant manner. So in theory, which you should recall from the other podcasts we've covered, in theory, a broadcast frame, or a frame to an unknown unicast address, as you should remember, those get forwarded out all interfaces except for the one it came in. So any of those types of frames will pretty much go around in circles forever unless we block somewhere. Uh, you can tell we're blocking because the orange lights mean they're blocking. These lights are not very reliable because we're blocking in more places than those two orange lights. So I would encourage you not to use the orange lights as your guide to whether you're blocking or not. So this week's lab, the first thing we're going to do is we're going to look at some spanning tree information, try to find our spanning tree topology. And I have two different VLANs set up for that, VLAN 2 and VLAN 3. You're going to find both of them. I'm just going to look at VLAN 3 stuff right now. So first thing you might want to do is basically just look at some spanning tree information. The command show spanning tree will show you the information about all your VLANs. So if we look at this, I have spanning tree stuff for this VLAN 1. Down here I have spanning tree stuff for VLAN 2, and I have spanning tree stuff for VLAN 3. Those are only three VLANs that exist. If you want to see a specific VLAN's information, you can specify the VLAN ID, and that just gives me the spanning tree information for VLAN 3. So a couple things we want to look at with spanning tree. A thing we might be interested in doing is determining the topology of our spanning tree. So a couple things to look at. Priority is used in the election of the root bridge. Whoever has the lowest priority wins. If there's a tie based on priority, then whoever has the lowest MAC address wins. So if you connect all your switches together and don't change any spanning tree settings, the root bridge will be the one with the lowest MAC address because they all have the same priority value by default. Cost here is 38. That is the cost from this switch to the root bridge. We will use the terms bridge and switches interchangeably in this discussion of spanning tree because a switch is really a multi-port bridge. So spanning tree existed with bridges, and then when switches came about, they just kept the protocol because it existed. So the cost is how much it costs to get to the root bridge, and this cost is based on the interface types that the traffic has to traverse. So in this case, I know the cost for a fast Ethernet interface is 19, so I know the cost to the root bridge is 2 hops of 19, so I know this switch is 2 hops away from the root bridge. This tells you which port the root port is, so if you want to try to find out where the root is for VLAN 3, then you can trace out the root port and see where this switch is connected to. I turned the port labels off because I was trying to look at the orange lights, which aren't being very reliable, so I'm going to turn those back on. Right, so it said 22 was the root port. Was I on the right switch? Which switch was on? Okay, I was on switch 0. So this says 22 is the root port for VLAN 3. So that tells me that to get to VLAN 3, here's port 22 is connected to this switch. So if I go look at this switch, it's not going to be the root port for VLAN 3. It's not going to be the root bridge for VLAN 3 because the cost was 38, which I said was 2 hops. So the cost on this guy is going to be 19. The cost is 19. Its root port is 23. So if we look at port 23 to this guy, this guy is going to be the root bridge for VLAN 3. And you can tell that because it says this bridge is the root instead of a cost, because there is no cost because it is the root bridge. So that's how you can figure out your topology. Another thing these commands show us is the state of the ports. So here are the different ports associated with VLAN 3. These 3 ports are trunk ports. This one is a user port, and it shows that these ports are all designated in forwarding. Forwarding means they're sending frames out. If we go back and look at this switch's ports, we have designated forwarding. These means it's forwarding frames out. Here it tells us the root port is FA0/23, and then we have port 24 is blocking. Remember, some of our ports in our redundant in our network with redundant links will be blocking. So this tells us that 24 is blocking. So no traffic is coming in or out 24. So that's some of the basic topology things we can look at with spanning tree. We are actually going to do some exercises where we cause a failure. So I'm going to get ready for that just to demonstrate it for VLAN, what's going to happen with VLAN 3. What I'm going to do is I'm going to make all these ports access ports, all the trunk ports access ports, but I also want to ping something continuously. And that's going to be, I don't know why those ports up there won't go away. They're annoying me. Anyway, we're going to ping this guy right here, 3.9. So we're going to ping from this PC to 3.9 in this case. So what we're going to do is we're going to start this ping, and then we're going to fail the root bridge. And by fail the root bridge, I just mean make it so that it can't be the root bridge anymore. I'm going to ping up so I can see it. And the way we're going to do that is we're going to make its trunk links not trunk. So I would set them as access. And now we're going to look at what happens on our ping. In theory, when you do this, you're going to start a timer. So we're going to wait and time how long this takes. I'm not actually timing how long it takes, but you should. It's probably going to take, I don't know, 50 seconds is what it should take. And why do I say it should take 50 seconds? Yeah, I don't know if it actually took 50 seconds or not, but I say it should take 50 seconds because based on our timers, that's what it should take. We have three different timers we worry about. We have the hello time, we have the and then we have the forward delay time. So when we detect a failure with a regular spanning tree, we wait 10 times the hello time before we do anything. So that's 20 seconds, and then we block for 15 seconds to let old MAC addresses time out, and then we learn for 15 seconds. So we end up spending 20 seconds before we decide to do anything, 15 seconds blocking, and 15 seconds learning. So that gives us a convergence time of about 50 seconds with the default timers. So that's how long I would expect it to have taken. It does take that long when we do it in class with the real equipment, but sometimes the simulator doesn't behave as real equipment does. So that may or may not work as expected. Here's the thing I think is interesting about spanning tree. So your network broke and it failed. We expect that. When things break, they fail for a little while and then they start working again. That's good. A weird thing about spanning tree to me is that if something breaks and you go back and fix it, or like say you realize, oh hey, somebody jacked up the root switch. Let's fix it. Sometimes when you fix things in a layer 2 network, is my ping working? Yeah, the ping's working. Sometimes when you fix things, right, you're fixing this. It was broken and you fix it. You make it a trunk. Oh no, you just fixed the network, but you really caused a momentary outage while the spanning tree network reconfigures itself. So just be aware that this can happen when you're fixing things, and you might want to, if you're screwing around with spanning tree or adding new switches or whatever, if having some downtime is a bad thing, like in an e-commerce environment. If you have some downtime for the users, they're probably going to not going to notice that little bit of downtime. But if you have some downtime in an e-commerce environment, they might notice. So I think you should just be aware that messing around with things that you don't think should have an effect on the network may have an effect on the network. So that's the first part of the lab. We're gonna mess around with doing that stuff.